We are going to start again with the class. So today we're going to be revising another type of test. So as I was mentioning, the normal distribution is something that we use very often. Like most of the times, we are assuming normal distribution. But in many cases, there are some other distributions that are extremely helpful. So one of them is the chi-square distribution. So we can perform the chi-square test for two different reasons. Well, among many reasons. So one is going to be the so-called goodness of fit, which is a very important test for your data, and the independence test. So I want to know whether A and B depend on each other. So so if that is the case, I need to test it, because what if I have two different variables, and one variable is how to say, like the double or half of the other? So they are clearly related. So they are not independent, they are dependent. So I want to test these two things, and I will use the chi-square distribution. So this chi-square distribution, you're going to find it everywhere in your computations. Next semester, you are taking econometrics, and every time you run a regression, the chi-square distribution probably will show up. Also, something that you have to keep an eye is the F distribution. So we don't have enough time to go through it, but this is also a very important distribution that is going to be useful when we are using many variables. So so chi-square might be used to look at two different variables. The F distribution, we have many variables, so we can find whether or not one of the variables is an scalar or is related in some ways with any of the other variables. So that's what we need to know. So in this case, we're going to use the chi-square test. And as I said before, in this today and Wednesday, we're going to complete these two topics. So if you want to keep looking at the slides, so this is very important. This is about the F distribution, and also what is known as the ANOVA. ANOVA is the analysis of variance. It's very important too. So so I don't want you to get confused with too many terms. Remember, this chapter is not going to be graded, and the test is not going to be graded. So please don't do it. If you do it and you think that you are doing a good job, I can give you some credits, especially those who are falling behind. But if you already have a good grade, and I mean, you don't have to do it. Do it in case that you really need to learn the materials, which I believe is very important. So having said that, so we're going to start with our chi-square distribution and the so-called goodness of fit. So so we're going to use the chi-square distribution to test whether a frequency distribution fits a claim distribution. So I have information from the past, and now I am taking samples. So for some reasons, I know that, as we are going to see in the next case, that people, like for example, if I am the manager of H&R Block, I know that 20% of the people use my services, 20% of the people uses Friends, and 30% uses some other methods. So I'm going to take a sample and see whether or not that is true. So I am assuming, based on previous experiments, that this data follows a pre-established distribution. I just want to confirm that my data fits that distribution too, which is expected. So I am expecting that the data that I am going to test follow the same distribution as the hypothetical in this case, right? So I have some experiments previous. Now I'm going to do my own experiment, and I'm going to see whether my data fits the distribution of the existing data. So so we are going to use what is called a multinomial experiment. So remember, we have these binomial experiments. So in the binomial, we have only two choices, the probability of success and the probability of failure. But now we are expanding this to many other more. So I can have three different cases, and I want to know whether that distribution fits the same distribution as in previous experiments. So multinomial expands the notion of the binomial. So we are going to be using percentages. So that's going to be what we are going to be doing. So the proportions now is not going to be only failure and success. It's going to be different categories. For example, I was mentioning you, we have people who do the taxes using electronic resources. Some people give it to their friends. Some people do some other things. So there are many categories in which people use tax services. So in this case, that is considered a multinomial experiment. So this is a probability experiment consisting of a fixed number of independent trials in which there are more than two possibilities outcomes for each trial. So the probability for each outcome is fixed. So that means that the probabilities existing are going to be always the same and they are not going to change. And each outcome is classified into categories. So, and we make the comparison with the binomial experiment where we have only two different possible outcomes. Here we have success and failure. In a multinomial, we have more than two. So we have to use something that is called the chi-square test in this particular case. So very simple, very simple. If you do it by hand, if you use your calculator, you might take some time in doing it. If you know how to set this, I mean, at this point, I will expect that even if I don't give you this, you will have the tools to build your own formulas, which are going to be formulas that are going to help you to solve this in less than 5 seconds. So, so in this case, we're going to look at a multinomial experiment. For example, a tax preparation company wants to determine the proportion of people who use different methods to prepare their taxes. So the company can perform what is called a multinomial experiment. It wants to test a previous survey claim concerning the distribution of proportion of people who use different methods to prepare their tax. So somebody else in the past published that study, that experiment where he was interviewing people, and people say, well, I asked my friends, I asked the company, I asked somebody else, blah blah blah. So so that's what we are expecting. So we are going to be comparing previous data with the data that I can gather, right? So it can compare the distribution of proportions obtained in the multinomial experiment with the previous survey's specified distribution. So in order to do this, we are going to use what is called the chi-square goodness of fit test. So that is a very common test. You have different proportions and you have previous data, so you can compare whether this is what you are expecting. So probably you are expecting a uniform distribution, and that doesn't behave as a uniform distribution. So in this case, we might believe that some distributions are skewed right or left or something like this. So we need to compare these results and see whether the data that we are gathering fits that particular distribution. So the chi-square goodness of fit test used to test whether frequency distribution fits an expected distribution. Of course, the null hypothesis is that the frequency fits the specified distribution, and the alternative hypothesis states that the frequency distribution does not fit the specified distribution. So always we are going to assume in our null hypothesis that what we are doing in our experiment fits previous distributions. And the alternative, of course, is going to tell me whether or not this is going to be true. So it's the counter argument, sorry. So so we have this, but it's a simple test. it's exactly the same idea that we have been doing before. We are gonna do the test statistics. In this case, it's gonna be a chi-square test, and then we are gonna compare it with the chi-square for the data. So we have a comparison between the observed and the hypothetical. So in this case, well, in this case is the observed compared to the expected, which is basically the hypothetical. So we are going to compare these two, and we are going to make sure that my chi-square answer that question. So this is what that's, I think I like more explaining the case than explaining the theory, but that's actually what happens. So this is the results of a survey of tax preparation methods. Somebody in the past did it. So each outcome is classified into categories. So we have the tax was prepared by an accountant. People did it by hand. Some people use computer software. Somebody else, a family friend, tax preparation services. And those are the percentages that they found in the past. So, so the probability for each possible outcome is fixed. So in this case, let's imagine that you have a tax preparation service. So you are expecting that 15% of the people in, let's say, in the neighborhood, they are going to look after your services because that's what you know, right? So you want to make sure that this is the case. You gather people information, you run your own survey, and then see whether what is happening now is what happened in the past. So the distribution is the same. So in this case, the distribution of tax preparation methods is 25% by accountant, 25%, 20% by hand, blah, blah, blah. So that is going to be the claim. The counter argument is that the methods differ from the claim or expected distribution, right? So this is the expected distribution, and we can say that those methods are not the ones. So so this is even simpler. So we are gonna use two different things here. We are gonna gather data from our own survey, and we are gonna keep the percentages that are from the previous experiment. So in this case, we are gonna build a table, as we can see here. So with the categories, with the expected or the expected proportions, and then we are going to build another one with the observed proportions. So, sorry, with the observed data. So, for example, if I gather my information, the observed, for example, I'm going to count how many people in my survey are using accountants as the method for preparing their taxes. So I'm going to have a number for those who choose by hand, and so on and so forth. So so in this case, we are going to find the following. So to calculate the test statistic for the chi-square goodness of fit test, the observed frequencies and the expected frequencies are used. So we have the percentages and we have the observed. So once we do the observes, I need to know what is going to be the sample size, because I'm going to multiply this sample size by these numbers, and I am going to get the expected share or the expected number of people based on the sample size. So it seems something very simple, and indeed is very simple. So the observed frequencies, we are going to recognize it by O of a category is the frequency for the category observed in the sample data. So in this case, we don't have the frequency, we just have the hypothetical values for each category. So we are going to run our survey, and we are going to find the observed frequencies. However, we also have the expected frequency. So we are going to represent this by an E. So this expected frequency of a category is calculated frequency for the category. So what I'm going to do, as I mentioned before, I'm going to count how many people in each category. So the additional column that I was mentioning, how many people are in here, and I am going to multiply the number of people in here by the sample size. So sorry, I am going to multiply. So let me go back. So the expected frequency. So I think I should go and show you what I did, because that is kind of like a tongue twister for me. So in this case, what we have is the following. So let me show. So this is the exact same example. So so we have well, probably I did something. What is here? So the distribution of the tax preparation. Let me erase all this information. So so in this case, 25% are done by accountant. Also, I highlighted this and I asked Excel to represent this in percentages. So I click here. So every time I'm gonna type a number here, this is gonna recognize the percentages. So the first one is 25%. The second one is 20%. The third one is 35% by computer software. Then by a friend is 5%, and services is 15%. So that is the data that I know, hand, accountant, hand, software, friend or family, and service. So that's what I did. That is what we are, the known probabilities. And then when I run my survey, so in this case, I have 300 people. So 71 of these people answered that they did the accounting with, sorry, they did their accounting with an accountant. 40 of them said that they did it by hand, so on and so forth. So I'm gonna put this data here. So I want to just tell you what I did. So before doing this, oh no, let's do this. So we have the observe. So when I do my survey, I have 71 people here. So I have 40 people here. I have 101 here. I have 35 in the next category, and I have 53 in the last one. So what happened is I have 300 people. That's what my survey is all about. I have a sample size of 300. So what I did is the following, going back to the previous thing. So when I want to find the expected, let me make this smaller. Let me put this in here, and let me erase this. Okay. So what I did here, so basically I made sure that all these things are 100%. So I added all these numbers. So also while I was typing these numbers, I make sure that they are 300. So I build this formula here. So now I know that my 5 categories are equal to 100%, and my sample size is going to be 300. So in order to find the expected, because remember, we are going to use the observed and the expected. So if I have 300 persons here, I need to find what is expected, which is the 25%. So I'm going to do equal, I'm going to do the sample size times my 25%, right? So that is going to tell me that out of these 300, 71 people said that they were using an accountant, but actually I was expecting 75. So that's what my known probability is telling me. So I can do exactly the same, 300 multiplied by 20%. So in the second case, I have 40 people observed. So I did my survey, 40 people answered that they did it by hand, but the expected was 60, right? So 20% of these 300 is going to be 60. So that is the expected, that is the observed. So I can do the same. So I just wanted to do a couple of them. But remember, if I put a dollar sign, because I'm going to be multiplying all these by the same thing. So I can just pull this down, right? So as you can see, the expected versus the observed. So I have 300 in each arm, which is something that I want, right? So this is based on my survey. This is what I am observing. This is what is based on the known probabilities. So let me go back to this. The expected frequency of a category is the calculated frequency for the category. Doesn't say too much, but expected frequencies are obtained by assuming the specified or hypothesized distribution. So this is the hypothesized distribution. So the expected frequency for the ith category, so this expected value is going to be the sample size times the probability that we know, right? So in this case, n is the number of trials, basically the sample size, and p is the assumed probability for the ith category. So this is the ith category. This is the category for accountants. So I'm going to multiply the sample size times the category of accountants. I did the same here. The sample size times the known probability for by hand, so on and so forth. So at the end, I know that I am right because I am having 300 elements in each arm, okay? So what does my my goodness of fit is all about? So we have this tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. So the results are shown at the right. Find the observed frequency and the expected frequency for each tax preparation method. So in this case, these guys are going to do what we did. So this is the observed frequency, the number of adults in the survey naming a particular tax preparation method. Then we have the observed, right? So this is the observed frequency. So to find the expected, as we did, we multiply the sample size times each of these probabilities, n times pi. So we have our expected and our observed. So so now we are going to start thinking about what is the next step. So this for the chi-square goodness of fit to be used, the following must be true. So the observed frequencies must be obtained by using a random sample. Of course, I need to do this as random as possible. How can I do it? Well, probably I will, I mean, like in the old times, I will check, I don't know, take some information from, or just go to the street and ask people how they do their tax preparations, whether they do it, and if they do it, what is the method they use. So I can find random people in some places, or I can do it by mail. I can identify people, I don't know, in the somewhere in a directory, and ask them how they do their their taxes. So randomness, always the most important thing when we are doing experiments. The absence of randomness or the absence of a random sample might yield, as we know, biased results. So also we need that each of the expected frequencies be greater or at least equal than 5. For sure here we have that all the expected values are greater than 5. But let's say that maybe one of those is going to be lower than 5. So that might not be good. So probably if one of the expected frequencies falls below 5, we cannot apply the chi-square test, okay? So we have to keep that in mind. So to perform the chi-square test, so we already have the observed and the expected. So we have to subtract the expected from the observed. We have to square it and then divide it by the expected, right? So I have the observed, I have the expected. So I'm going to subtract the expected from the observed, square it, and then divide it by the expected. So what I'm going to do here is I'm going to build a formula, which is, I'm going to open a parenthesis, and I'm going to say the observed minus the expected, then I'm gonna square it to the power of 2, and then I'm gonna divide it by the expected. So that is my first value. So once again, so let me press enter. So the observed minus the expected, then the difference is gonna be squared, and then it's gonna be divided by the expected. So once I solve one of the cells or one of these differences, I am gonna do for every single one, and then I am gonna add all the values. So that is gonna be my test statistic. That is gonna be my chi-square statistic, okay? So some things that we need to know, if these conditions are satisfied, that we have a random sample and we have so we have a random sample and we have that all the values in the expected are bigger than 5. So if these conditions are satisfied, then the sampling distribution for the goodness of fit is approximated by a chi-square distribution with k minus 1 degrees of freedom. So remember, when we are for some distributions, we need the degrees of freedom. If we are using the t distribution, we need the degrees of freedom. If we are using the chi-square distribution, we need the degrees of freedom. In this case, the degrees of freedom are gonna be the number of categories. For example, we have 1, 2, 3, 4, 5. So in this case, k minus 1 is 5 minus 1. So I am gonna use, let's say, a 1%, so a 1% alpha with 5 categories, but the degrees of freedom is gonna be 4. So that's how I am gonna build my chi-square critical, right? So let's keep doing this because this is a little bit different. So first of all, so we are gonna subtract the observed minus the expected, square it, divided by the expected, then do for every single one, and then add all of them. So that is gonna be the value of my chi-square. So where O represents the observed for each category, if E represents the expected frequency of each category. So we know these values. So we are gonna pull this down because I am just figuring values in this. So I'm not using any fixed values. So I'm gonna go down. So those are the values for my chi-square. So so the observed minus the expected square for the first one, for by hand, for software. So I am going to add all of them, and I am gonna get a value. So this is the test statistic. So this is the value that comes from my data, right? So now all I have to do is to compare this value with the chi-square critical, right? So I am gonna use the alpha and the degrees of freedom in order to compute my chi-critical. So in this case, there is an Excel function that is chi-int, chi-imb. So all I need in this formula is basically the probability, so in this case, 1%, and the degrees of freedom. So if I put these values in my chi-square critical, I am gonna find the critical value. So to make the long story short, so this is how we do it step by step. Let me skip that. So so we have this, we did it. So so we have a 1% level of significance. We have a 5 categories. So degrees of freedom are going to be 4. So if we use the chi-square tables, so we are going to find these values. So so something that I didn't mention, I guess it does mention lately. So or probably I skipped it because this is only a right tail test. So in this case, let me see if I skipped it. But very likely we're going to be using a right tail test. So meaning that when I am doing this, So let me draw my map, my distribution. So for the chi-square, so I'm gonna remember the chi-square is kind of like skewed right. So my chi-square critical is 13. So once again, this is gonna be always a right tail test. So my chi-square critical, let's put a C, use a C, is gonna be 13.277. And my chi-square test is gonna be something here, 35.1, right? So the rule that we already know, if the test statistic falls in the rejection region, so we reject. If the test statistic falls outside of the rejection region, we fail to reject. So in this case, we are going to reject H naught. So let me, so I was looking for that statement because that is very important. I didn't see it, but basically all these are going to be a chi-square distribution that is always a right tail test. So so remember, so well, so it should be a right tail test. I don't find the statement, but it should be somewhere in here. So okay. So in this case, we have so the case, we have the hypothesis, we have the claim, and we have the chi-square distribution. So because we are rejecting the claim, so there is enough evidence at the 1% level of significance to conclude that the tax preparation methods differ from the previous survey's claim or expected distribution. So that might be important because I might be hoping that some of these, like for example, if I have a tax service, I would like to know how these numbers are. So whether my numbers are more, I don't know, because they are different. I am saying that my distribution is different from the claim or the expected distribution. So so that's very easy to know. So so in this case, very simple test. I guess all the math behind it. So we have to do a lot of math, which is very trivial, but is kind of time consuming. So in this case, what we did is we just built a formula for each one and then did the summatory and then use also a Excel function to find the critical value for the chi-square. So I don't have to use the tables. I just use the chi-square, the app, I don't know what's going on. So we just use the Excel function. So that's what I was planning to say. So in this case, very easy test. We have another case. For example, that probably is not that clear, or probably is clear because we have a distribution. I'm claiming that the distribution is the same, and I realize that it's not. So we have a second case. In this case, we are assuming a uniform distribution, which is almost like a rectangle. So if we have to do this distribution here, so very likely we're going to have a distribution that looks like this. So just imagine that you have a bag of M&Ms. So those are the chocolates, right? So, and we have brown, yellow. This is brown. This is yellow. This is red. This is blue. this is orange, and this is green, right? So when you buy your M&Ms, you probably are expecting that every time you open the bags, you're gonna find the exact number of brown, yellow, red, blue, and orange and green. So that's what you are expecting. So you are expecting that this distribution is gonna follow a rectangular distribution, or so-called uniform distribution, right? So we talked about this distribution previously. So I pick any bag, and I am expecting that I'm gonna find this. So the observe has to be that every single color is gonna be exactly the same. But when I pick one of the bags and I count the number of M&Ms of each color, I can find something different. So in this case, we have this case. So a researcher claims that the number of different color candies in bags of dark chocolate M&Ms is uniformly distributed. We are expecting that, and I think the company is expecting that. So to test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. So the results are shown in the table next slide. So we are gonna use a 10% level of significance to perform a chi-square test. Let me use all. Okay, so we are gonna use a 10% significance to perform a chi-square goodness of fit test to test the claim or expected distribution. So I know that this is the or that is the expectation, but then I open the bag and something happens. So the expected basically in this case, well, so in this case is the observe. So if I open my bag, so I'm gonna have 80 brown, right? I'm gonna have 95 yellow, 88 red, 83 blue, 76 orange, and 78 other color. So if I add this, of course, it has to be the 500 that I am expecting. So this is the 500 I am expecting. So I have 500 candies in a bag. So the expected basically is gonna be, because it's uniform, a uniform distribution, so it's gonna be how many categories we have? We have 1, 2, 3, 4, 5, and 6. So I'm gonna say we have 500 divided by 6. So I am expecting that all of them are gonna be the same number. So that's what I get. Okay. So in this case, let me erase the zeros. I don't need zeros here. And in this case, I don't need too many decimals. I'm gonna use only 1, right? So once again, I open a bag and I find 80 browns, but there should be 83.3. Of course, you are not gonna find 83.3, but that's the expectation that you have based on the distribution of this, right? So you are expecting that all of them are the same. So you open the bag and find 95 yellow, 88 red, so on and so forth. So once again, we are gonna use the same formula. We are gonna subtract the expected from the observed. We're gonna square it and then divide it by the expected. And then that is gonna be my chi-square distribution. So this is my chi-square test statistic. And then at the 10%, level of significance, we have 1, 2, 3, 4, 5, 6. So I have 6 categories. So I have 5 degrees of freedom. So this is gonna be my chi-square distribution. So let me go a little bit higher here. So what we have here is the following. um, so remember, my chi-square is a distribution that is skewed right. So my chi-square is going to be, let's say, 9.23. So this is my chi-square critical equal. So I need to figure this out, and I need to know whether this is inside or outside of my um, um, rejection region, right? So in this case, what I'm gonna do, once again, I'm gonna build my formula equal the open a parenthesis, like in this case, then the observed minus the expected, close parenthesis, squared, divided by the expected, okay? So we have a value. So I'm gonna drag this down, and my chi-square distribution, the chi-square test statistic is gonna be 3.16. So here I have a number that my chi-square is 3.01, right? So that means that this is outside of my rejection region. So I am gonna fail to reject my I'm gonna fail to reject my my H naught. So I'm gonna fail to reject H naught, and H naught happens to be the claim. So I don't have enough evidence, or I have enough evidence to, there is not enough evidence at the 10% level of significance to reject the claim that the distribution is uniform. So in this case, so once again, this is the test statistic. This is the alpha. So this is the level of significance.
Professor,
Yes, who is this?
this is Terry. Can we see the formula again? Because I got different numbers. I don't know if I used the right numbers for
Which
uh
one?
the
In the,
O minus E squared minus E on the brown, yellow, red, blue, orange,
oh,
green.
here?
Yeah.
That might be possible. This is the, oh, what happened is, I guess I just changed, well, but I don't know. Are you getting different numbers?
Yeah.
Well, technically speaking, shouldn't be,
My
but
expected
probably yes.
my expected is my expected is 80 and my observed is 83. Well, okay, maybe they put it in wrong backwards. All right. All right. Never mind.
Well, that's what I was gonna say. I changed the labels after I sent this. So just relabel it, because I made a mistake.
Okay.
Well, not I didn't, but of course I make many mistakes, but I just thought that it was easier for me to do this. So yes, in the past I said expected, observed. So probably that's the reason you have changed it, because you are dividing by a wrong number. So
Okay.
because the difference is always the same, and because it's a square, it doesn't make any difference, but you are dividing by something different. So please correct it. And in this case, so we have a very clear case. So we are claiming that the candies are uniform. So I open that bag, and I realize that they are not uniform. So probably if I am the manager of that, of the production process, I'm gonna say, guys, what's going on? I mean, this is too much. This is too much difference. So for example, this is almost 12 difference. This is like 7. So quality control might be something that you should claim in this case, okay? So is this clear so far? So basically that is almost half of what I wanted to say. So this is number 30. I think time flew by very fast. So I will leave something for next class. I guess I am going to stop here. Well, no. Let me just introduce the next one, because the independence test, as you can see, even though, well, before continuing here, so what happens if I have more distributions? Of course, I want to use the same. So probably I am gonna, let's say that I have 11 different categories. So I'm gonna insert. So probably I'm gonna, hold on. So let me edit, do autofill. So let's say that we have a color that is called ZZZ, a color that is called DDD, and a color that is called FFF, right? So, and I have more values here. So I can use this just by modifying, if I know of another rectangular distribution, probably I can use still this. Or if I have another type of distribution, like more categories here, I just can insert some columns and just copy the formulas and see what happens. Like for example, here, I think it's easier. Let me insert 2 columns. Oh, I think I did the opposite. So let me, or probably I want to make it smaller, but let's say that I want to insert some rows. So I have a process that is called DD and a process that is called XX. So probably those numbers are going to be modified. Probably this is 15%, 15%. This is 2%, and this is 8%, right? So I have different numbers. Probably I get here some 10 and here 30. So this is fictitious data. So what I'm doing is I am multiplying, I am using the same scheme to find these values. So as you can see, I'm just pulling, dragging these cells. So in this case, as you can see, there is nothing here, but I have a formula here. So I'm just gonna click. So it's gonna be very easy for you guys to just keep entering or leaving things out. So in this kind of cases, it's gonna be easy to add or to erase some of the procedures. So my point is, if you have more than 5 categories, so you can still use this, but you can, or just building the formulas. I don't think the formulas are difficult at all. So so just look at the formulas, build your Excel file, and that's what you have to do. So so this is very easy. Let me continue with this. Let me see, what can I do? So actually, there are like 50. Okay, well, I can do just a couple of things today. So this is very important because once again, I want to know the distribution, whether the data that I have in my survey matches the expected distribution. So in this case, it's clear that, of course, if I buy a bag of candies, I know that all the colors are going to be uniformly distributed. So I open the bag and happens not to be the case. So in the previous case, we have a different distribution. I don't even know exactly what kind of distribution this is, but I want to see how much my data differs from the previous. So so I can run that test, and that test is going to be very, very informative. So that is called the goodness of fit. So in a regression, when you are doing regressions, so this is one of the first tests that you need to run, because you need to know whether the underlying distribution fits the data. So that is a very important test for your future work. So in the second case, we are going to use another test that is called the independence test. So so we are going to use the so-called um, um, contingency tables. So in the first case, we have a very simple table. So we have a table with known probabilities and the observed probabilities. And we have only, let's say, a one-dimension table. But what happens if I can stratify these in different categories? For example, well, you will see. So in this case, we are going to use what is called contingency tables to find the expected frequencies. And we are going to use the chi-square distribution to test whether the two variables are independent. So independency is a very, very important test. So just imagine that one depends on the other. Like, for example, you have data on, I don't know. So let me open. So you have A. So you have a variable that is going to be called A and a variable that you are calling B, right? So A is 1, 2, 3, 4. And let's say that this is 5. So that's the data I have. So you have another data, another variable that is this same column, but the double. So basically this data is not independent because the values here, the values in B are changing when the values in A are changing. So they are in certain way connected. So that is a problem with the data. So I need these two variables to be independent. So in order to perform any computation. So in many cases, when the data is not independent, we cannot do certain type of tests, okay? So we are gonna use what is called contingency tables. So we are gonna have rows and columns. So this contingency table shows the observed frequencies for two different variables. So the observed frequencies are arranged in R rows and C columns. So the intersection of a row and a column is going to be called a cell. So remember when we were looking at the probabilities and we mentioned the conditional probabilities. So being a male and being in the nursing program. So something more or less here we have rows and columns and the intersection of both is going to be called a cell. So this is the case. That's a very simplistic case. The contingency table shows the results of a random sample of 2,200 adults classified by their favorite way to eat ice cream and gender. So you go to the street and you ask 2,000 people, 2,200 people, whether they are male or females, and then whether they have ice cream in a cup, in a cone, in a sundae, on a sandwich, or in other forms, right? So I like the banana split. Probably that will fit my category. So this is the results of my survey. For example, this survey can be like in this case. So we have a subject, but it's going to be 1, 2, 3, all the way down to 2,200, right? So one of the questions that people are going to answer is going to be gender. So I'm going to have female. The second is going to be a female. The third is going to be a male. Another male. So we have different things. So we are going to have here another column that says ice cream. So this female likes to eat in a cup. This female likes to eat in a sundae. Something like this. So we are going to have 2,200 observations with gender and ice cream. So at some point, when you are using other programs, this is very easy to compute. So tabulate this is going to be a no-brainer. So it's going to be very easy. You can produce a table with 2,200 variables by using technology. So, but in this case, very nice example. They are giving us the observed um, um, the observed values. So we are going to the street or we are asking people via internet. I probably use Facebook and I said, hey guys, are you a male or a female? Do you like to eat ice cream in any of these categories? So the data is going to be collected very rapidly, probably not efficiently because might not be the best randomly uh, the best random case, but it can do the purpose. So probably if I am the owner of, or so one of the managers of these big companies that I don't know the name of any ice cream company, but they probably will run surveys in a more randomly way. So so this is the data. So we have males eating eating ice cream in a cup, females, so on and so forth. So in this case, to find the expected, that's gonna be a little bit how to say not very difficult, but it takes a little bit of time to figure this out. So assuming two variables are independent, you can use the contingency table to find the expected frequency for each cell. So the expected frequency, remember in the previous case, was the sample size times the probability at this particular point. So here, the expected frequency is going to be the sum of the row that multiplies the sum of the column divided by the sample size. Is that a tongue twister? Probably yes. Let me do this here. So we have, so this is the expected. So first of all, let me raise this. So let me, well, I'm going to keep this. So at the end, the expected and the observed have to be the same. So first of all, let me enter this information in my table. So I need to know how many, so what are the values? So I reproduce this table. So all you have to do is to reproduce this table. So, so we are gonna say there are 600 males. To make this nice, I ask Excel to add my column and then to add my row. So according to my formula, I need the sum of the rows, and I need the sum of the columns. I have to multiply them and then divide by the sample size. So in this case, I'm gonna build my table. First of all, I'm gonna build my table. I have 410 here. So I have 1,010 people who eat ice cream in a cone. So in this case, 600 are males, 410 are females. So when it comes to cones, 288, and here is 340, right? So the Sunday is gonna be 204, 180. Ay, Dios mío. 204. Something happened here. So custom, I want numbers. And I want numbers without, okay. So sometimes when you get something weird here, like for example, I type something and probably the cell was recognizing a date. So I have to go to general, to this number. So you are setting up your preference for numbers. So this is general. So sometimes you need the percentage, you need the fraction, the scientific. So in this case, because this is data, I use the number, right? So sandwich 24 and 20, and others, So if you can erase this in your Excel file, please do so. We are gonna build the formula again. So in this case, other is gonna be 84 and 50. So at the end, I have 1,200 people that are males. I have 1,000 people who are females. In total, I have 2,200 people. So out of these 2,300 people, I have 1,010 that eat ice cream in a cup, 134 other sandwich, 44. So we can look at the data and see what's going on. So in order to build the expected, and probably I'm going to stop right there and I'm going to let you do it. Please erase this and try to do it by yourself. It's not such a big deal, but that might help. So we are going to multiply the sum of the rows. So this is the sum of the rows times the sum of the column, and then divided by the sample size. In order to get this number, I'm going to say equal. I'm going to open a parenthesis. I'm going to take the sum of the rows, multiply it by the sum of the columns, and then divide it by the sample size. Okay. So far, I can tell you that this is going to be a number that is going to be always the same. So I'm going to multiply everything by the sample size. So that is to find this observation. To find the second observation, I'm going to do the following: equal the sum of the row times the sum of the column. In this case, the column is different, so it's the second column. So I'm going to divide it by the sample size. So I can do it one by one. So or I can do the following. So I know that this number is going to be always fixed, and I know that this number is going to be always fixed. So what I'm going to do is I am going to fix. So I'm going to be moving across. Let me think. Well, let's do it one by one. You probably will find a better way to do it. So to do the third, I'm going to do exactly the same. The column, the sum of the rows times the sum of the column, in this case is the third column, divided by the sample size. So once again, the sum of the row, the sum times the sum of the column divided by the sample size, right? And then finally, I have this, which is going to be the sum of the row times the sum of the column, in this case 134, divided by the sample size, right? So as we can see here, we have 1,200 males, which is good. So we basically did this very easily. So if you find a different number here, that means that you probably miscalculated something. So the observed number of men has to be exactly the same as the observed number of women. So here, I'm going to do the same for the second. So the second is the sum of the column, sorry, the sum of the row times the sum of the column, the row times the column. But we are in the second, we are for females. So now we have the sum of the rows for females times the total of the sum of the columns, and then divided by the sample size, right? So so we observe 600 people buying ice cream, 600 males buying ice cream in a cup, and 410 females. So what we were expecting based on this distribution is that 550, 91 and 450, 909. So that's what we were expecting. So I don't need the totals. I don't care too much for the totals here. I care for the totals here, right? So I want to make sure that these numbers are the same. Probably I can find the totals here too, but as long as I get the 1200 and the 1000 here, I will be okay. Second column, I'm gonna do once again the sum of the rows times the sum of the columns divided by the sample size. So equal row times column divided by sample size. Now we have the same equal parentheses rows times column divided by sample size. And the last one is going to be rows times column divided by sample size. Okay, so once again, we were expecting 84. Sorry, we observed 84. We have 7309. So we have 1,200 people in our survey. So we have 1,200 males, 1,000 females. So our computations are fine. Here we are fine because we have the same type of people. So that took a little bit of time to build this. I think what I would do here is that I am going to be using this, let's say in the first column, I'm going to be using this fix, this also fix, and I'm going to be using the sample size in all of them. So what is going to be changing is going to be the column. Hold on. In this case, the column is the second, right? So I'm going to use this. So what is going to be changing is the column. So in this case, I'm going to make this fix. So this is going to be the same. This is going to be the same. And what is going to change is this. So in this case, I can say, okay, return. So next one is 342. Let's say that, yeah. So so I just build this formula. The column, sorry, the row is going to be always the same as well as the sample size. So all that is going to change is going to be the column. So when I build this formula here, all I can do is just do it across, right? So in the second case, let me do it again. I'm going to say equal. I'm going to say the rows times the column divided by the sample size. So once again, this is going to be always the same. So I'm going to put a $sign. And this is always going to be the same. The sample size is going to be always the same. What is going to change here is going to be also the columns. So what I'm going to do is I build this formula and I just drag this to the left, right? So we built our expected. So next class, I'm going to do this. So once again, we are sure that my values are exactly the same. So the sample sizes are the same. So the observed and the expected have to be of the same size. So next class, we are gonna look at how to build the chi-square distribution. And if you are a little bit curious, so there is another thing that you can do, a test for homogeneity. So there is an explanation here. If you are curious about that, I might advise you to just have a look at the Khan Academy video, and we're gonna solve this also very fast, okay? So is there any questions so far?
Yeah, I have a question after class.
Okay, sure. So let me stop the recording. So what